Hey folks, and welcome to today's lecture. So starting today, we are working on an entirely new unit called molecular orbital theory. I'm personally really excited about this because it's the first time in PChem where a lot of our hard work on trying to understand wave functions and orbitals is going to come into play to help us understand what feels like real chemistry, the interactions of molecules with one another to understand better their bonding behavior and their reactivity. And so for the next couple of lectures, we're going to orient our discussion around a topic of great practical interest called small molecule activation. And so actually, before you watch any farther in this video, if you haven't already, go ahead and read the editorial article that I posted on Moodle on small molecule activation from the Journal of Inorganic Chemistry. And once you've watched that, then go ahead and come back to this video and we'll chat about the context of this and how it's going to help us dive into this topic of molecular orbital theory. Okay, hopefully you liked the article as much as I did. It's always nice to see scientists be really excited about their subject. And the opening question that's going to guide us for today's discussion is, if small molecule activation is a field of chemistry that seeks to understand the reactivity and possible transformations of molecules like water or oxygen, nitrogen, carbon dioxide for climate change, NH3 ammonia for this Bohr-Haber cycle so we can make fertilizer, or H2 so that we can transition away from using gasoline-powered cars to hydrogen-fueled vehicles. Well, if we want to understand these molecules, we're going to need a good theory that explains their chemical and physical properties. So in G-Chem and in O-Chem, we spent so much time trying to understand Lewis theory that this should be our first go-to. Is Lewis theory going to be enough for us to be able to understand the behavior of these molecules? If so, great, we're done. If not, we're going to need to develop a more substantial, more wave function or Schrodinger equation-based approach to understanding these systems. So our first question that I want you to answer on a piece of your own scratch paper is to draw the Lewis structures of O2 and N2. Based on your structures, I want you to predict whether or not each of these molecules would be diamagnetic. Remember from our last lecture, that means that that molecule would have no unpaired electrons. Or would you predict that it's paramagnetic with at least one unpaired electron? Go ahead and pause the video and answer this question. All right, so for me, drawing these Lewis structures gave me a structure for N2 that features a triple bond between the two nitrogens, each of the nitrogens having its own lone pair. And for oxygen, similar, but instead we wind up with a double bond and each oxygen having two lone pairs. And what's important to note about this Lewis structure prediction is that neither of these molecules features unpaired electrons. So Lewis structure says that both N2 and O2 should be diamagnetic. Now that we have our Lewis structure prediction, let's compare to experiment. And the way that we're going to do this is you are going to now again pause the video, and there's a separate YouTube video that I've posted both on Moodle and below in the comment section in the video description for how to do the experiment to determine the magnetic behavior of both of these molecules. Pause the video and go ahead and watch. So now that you watched the video, you probably see the bad news, which is that Lewis structure can't predict whether or not the electrons in O2 should be paired or unpaired. And if it can't predict where the electrons are, it gives us much less confidence that it will be able to predict the reactivity of this molecule. Okay, well maybe it's just O2 that was an issue. So let's try and use Lewis structures one more time for some of the other molecules on our list. I want you to draw Lewis structures for H2, H2O, and NH3. And based on these structures, I want you to see what information you can glean about how that molecule will be expected to react with ammonia. What about water? And what about H2? Pause the video, and when we come back, we'll talk about these Lewis structures. All right, so for NH3, we see that our nitrogen is bound to 3 hydrogens, and in order to account for all the electrons in NH3, we need one additional lone pair. So looking at this compared to a molecule like, say, water, which has 2 hydrogens and a couple of lone pairs, Lewis structures help us understand what possible reactivity might occur between our water molecule and the ammonia molecule. From your organic chemistry class, you probably remember that this lone pair can donate to the hydrogen, giving this oxygen even some more electrons than it already has, and ultimately what we could form from this reaction, although it's a weak base, not a strong base, we could form an ammonium cation and hydroxide. So far, so good. The real issue, I would say, is that while I can draw a perfectly fine Lewis structure for H2, I would argue that with H2, it's such a simple molecule. I don't see any lone pairs on H2. I'm not sure where the regions would be for positive or for negative partial charge regions of electron density. And so I would not be able to make any claims, really, about how H2 might interact with NH3. And that's a huge issue because, as we're going to see a couple lectures from now, NH3, or derivatives of this molecule, are actually very good at activating the H2 bond. And so while Lewis theory is not necessarily wrong in this case, it can't help us predict the reactivity. And if we can't predict reactivity, it's really hard to move towards rational design for new and better ways of activating certain small molecules. And so because we have, and this is just 2 of many examples where Lewis theory is mispredicting or unable to predict something about a molecular system of interest, we're going to need a better and more robust theory. And that is our motivation for today's lecture. In today's lecture, we're going to introduce to you the basic principles of molecular orbital theory. It's a wave function-based approach to understanding molecular bonding. We're going to talk mostly today in general terms, but we're also going to focus our attention on predicting the stability and the molecular bonding behavior of H2. And just as an extra bonus, we're also going to talk about helium. Why is it that helium is only observed in nature as a monotonic species, so just He, never He2, but H2 always seems to prefer in nature to be present as a diatomic molecule rather than as a monotonic atom? That's what we're really going to talk about today. And if you'd like to learn more about this topic, I encourage both reading Atkins topic 9b and 9c 1a in your text to go along with today's lecture. And then there's a number of ChemLibreTexts articles that I'm going to post on Moodle that I personally found really helpful in helping visualize some of the concepts that we're going to go over in today's discussion. Okay, let's go ahead and get started. I think it's useful at this point to briefly review some of the main takeaways that we had from our atomic orbital theory when we talked about hydrogen and that hydrogenic wave function, because those ideas are going to come back to the forefront when we talk about the H2 molecule. All right, review item number 1. Remember that a hydrogen atom has 1 electron placed in a 1s orbital. And furthermore, because we solved the Schrodinger equation, we know what that wave function for that 1s orbital looks like. It's a couple of constants times a decaying exponential, where, if you remember, A0 represents a Bohr unit of length. And the energy of that hydrogen orbital is negative half a Hartree, or if you like it in units of joules instead, negative 2.18 times 10 to the negative 18th joules per atom. So we're going to talk a fair amount today referencing this E sub 1s, and what I mean by that is that's the energy of an electron in a 1s orbital in an isolated hydrogen atom. A second big takeaway from our discussion of the hydrogen atom was how we graphically choose to represent wave functions. And there was 2 main ways that we chose to represent these, especially when it came to trying to draw these by hand. And so Two of our ways are, one, in purple I've shown a 2D representation of this wave function. This is me plotting, or sketching rather, psi 1s versus r. So this is the shape of the wave function. A second way of depicting this would be a boundary surface diagram, shown in blue, or a contour plot. And with this contour plot, remember, we lose a lot of information about the wave function. There's no way to depict its magnitude within this region, but you can see sort of where are the main regions of electron density and where is the electron less likely to spend its time. And in particular, with these boundary surface diagrams, normally you draw the boundary surface such that 90 or maybe 95, depending on what convention you're using, percent of the electron density is found within the boundary surface, and 10% of the time the electron is outside of this region. And then last but not least, sometimes folks will try and combine these two diagrams together so that you can see the shape of the 1s orbital depicted as a function of our nuclear coordinate, which I'll try and put a big dot here to represent. This is the nucleus of our H atom. And just like the purple graph, you see that decaying exponential, but because they're trying to depict this now in Cartesian coordinates, so this might be along the x-axis, that means that our orbital is going to have a symmetric decay both to the right and to the left. And so from here on out, we're going to start drawing the shape of this 1s wave function along both sides. And that's simply because our radius is symmetric along both directions. And then last but not least, we discussed in earlier lectures how for the wave function, it doesn't apply to the 1s orbital because it's positive everywhere. But for wave functions where psi changes sign, basically every other orbital besides the 1s orbital, we represent the different signs of the wave function if we're drawing by hand, usually using shading. So I've shown in purple a hand-drawn way of looking at a 2p orbital. The unshaded lobe and the shaded lobe both represent high regions of probability for the electron to be located in a 2p orbital. The only difference between the shaded and the unshaded lobe is that this represents that on the left-hand side of my graph, the wave function is positive, whereas on the right-hand side of my graph, the wave function is negative. And remember, when it comes to the electron behavior, the sign of the wave function isn't super important because it's psi squared that we're interested in. But you'll see later today that when we start combining wave functions, it's important to know their sign so that we can assess whether those wave functions are going to get even more positive by adding positive plus positive or cancel each other out by having positive plus negative. If you're drawing these or computer rendering orbitals, frequently folks will use two different colors to represent the same idea. So shading or colors can both be used to represent the different signs of the wave function. And with that, we're ready to talk about molecular orbital theory. So I'm going to start our discussion to try and make it as simple as possible by talking about the H2 plus molecule. So we've got one electron, two nuclei this time. And I should start by defining a couple of parameters that'll show up in the problem and a couple of variables. The big parameter for this problem is capital R, the bond length. And I've used the letter R so many times, so I should clarify that in this case and for this lecture, capital R is going to represent the bond length of my H2 plus molecule. Something around the area of an angstrom, but definitely this is not in this lecture representing the radial wave function or any of the other uses of capital R we've seen before. Because I have my electron, I should note what its coordinates are, what its relative coordinates are with respect to both my first hydrogen atom and my second hydrogen atom. So I'm going to, since I have two hydrogen nuclei in this case, I'm going to label one of them H sub A, so atom A, and one of them H sub B, hydrogen B, atom B. And consequently, my distances between the hydrogen and the electron, are RA and little rb, representing the distances between these. when we solve Schrodinger's equation, we're going to treat this bond length as fixed and allow it to vary as a parameter, much like how in our particle in a box example, we allowed L to be a parameter of the model. We could decide to change it, but we're not solving for big R. We are solving for little RA and little RB. So the ansatz, the big idea of molecular orbital theory, is that for this H2 molecule, the electron should spend some of its time, really half of its time, since there's no difference between HA and HB, half of its time on atom A and half of its time on atom B. In quantum terms, several lectures ago at this point, we termed that a superposition of states. And a superposition of states in quantum chemistry means that we're going to take a linear combination of the two different states that the electron could be in. So in this case, there's two appropriate linear combinations for my electron in the H2 plus molecule, spending some of its time in the 1s orbital on atom A, some of its time in the 1s orbital on atom B. Now, I've put an equal coefficient in front of both of these, just a universal normalization constant, n, and that's because we're spending equal time in both atom A and close to atom B. But linear algebra alone, or the superposition ansatz, doesn't tell me if the appropriate sign to put in between these two terms should be a positive sign or should be a negative sign. And so, in fact, we see two different options, and why we see those you can either treat as an ansatz or as a follow-up of superposition. This is sort of the limits of what we can say just based on our superposition argument. Or if you like and you've taken a linear algebra course, you could say that this is a basis set transformation. Going from an atomic basis to a molecular basis. So it could be viewed as a basis set transformation. You could view it as a natural follow-up from the principle of superposition. Or if you like for today, you can just treat this as an ansatz, where ansatz is a fancy term for just a given axiom of how we're going to start out this problem. In both cases, I need to make sure my wave function is normalized, and so I'm going to throw a normalization constant in front of both of these wave functions. It's not too difficult to normalize this problem, but it's also not important to the concepts we're going to discuss today, so I'm going to leave this n constant kind of by itself. Always when we see a new function, the best thing we can do is try and visualize it right away. And so let me show you a couple of different visualizations of what this psi plus and psi minus two new wave functions look like. First, we're going to talk about our psi plus wave function, which is shown here in purple. And so for our psi plus wave function, we are taking two separate hydrogen atoms, and we are slowly moving them closer and closer together. When they're far away, there's going to be no difference between, the 1s orbital on hydrogen A and the 1s orbital on hydrogen B are going to look identical. They're going to look very separate. But as they start to come close together, they'll begin to constructively interfere. And what that means is that as I add together these two functions, I'm going to start to see a region of increased electron density, as shown in this region right here. And mathematically, what I am doing is I'm simply adding together my original two wave functions. So if I can try and do my best of sketching these out, here are my original two wave functions. And because I'm taking this first function plus a second function, that's why my overall wave function is much bigger than each of these two tails individually, and that is going to overall give me the shape of the curve that you see depicted in this graph. And what I really like about this graph is it's showing you both the two-dimensional representation using the purple lines, as well as also showing you what the resulting contour plot or boundary surface diagram looks like, shown in orange. And once I put together two spheres, the boundary surface between these is going to merge. And because my tails are slowly adding together as well, it means there'll be a little bit of extra electron density that gets lumped in with my boundary surface diagram. And that leads to a final picture of what my psi plus orbital looks like for this hydrogen molecule problem. Now you'll notice this diagram uses terminology sigma sub 1s. That's terminology we'll start using next lecture. However, for now, we're going to call this just our psi plus orbital. And so this is kind of a static picture of what this looks like. I find it really helpful, once again, to use a computer visualization in order to think about this. And so what I've shown here is an applet that I've posted the link to on Moodle so you can play around with it. And this applet shows us, as a function of the internuclear distance, or our bond length, or the separation between these two nuclei, how our wave function, our molecular wave function, is changing. And it's pretty neat to see. So I'm going to slowly move the separation slider to the left, and it's going to take and put together closer and closer my two nuclei. So you can see at first, nothing really seems to be happening, again, because I'm just shifting these two sources of electron density slowly closer together, and at this point, the tails are not overlapping very much. It's a little small to see the text, but this corresponds to a separation of about 8 Bohr, or 4.2 angstroms, so much too big for what this H2 bond should look like. As these draw together, however, our region of electron density in the internuclear region, or between the two nuclei, starts to merge. And once we get closer to what the true H2 plus bond length looks like, we're going to start to see this lozenge-shaped picture emerge, which is what you see to the right in my more static picture that I drew originally. And so this is one, I would say, of the most difficult visualizations that we need to do in this course, is being able to look at a boundary surface diagram, or two boundary surface diagrams that are separated from one another, mentally put them on top of each other, and see what the resulting overlap would look like, and draw a new boundary surface diagram that relates to it. But hopefully, if you're able to play around with this applet a little bit, I can convince you that two spheres that are partially overlapping in their electron density, all with the same sign for the wave function, is going to look kind of oval-like or lozenge-like in its behavior. And so this matches up pretty well with what our electron density looks like in our static picture. This distance right here at about 2 Bohr, or 1.05 angstroms, that's where our traditional H2, neutral H2 bond length would be. Okay, so that is our sigma plus orbital. Again, it's really important to note in this picture that these positive signs that you're seeing don't represent charges. They represent the sign of the wave function. Okay, what about our sigma minus orbital? What does that look like? Well, just as before, we are taking two 1s orbitals on our different atoms, and we are merging them together slowly over time. The difference in this case is that instead of adding the two wave functions together, I'm going to subtract wave function B from wave function A. So you'll notice that in this green picture that my first wave function on atom A is unchanged, purple and green are the same, but this second picture is the same shape of the wave function, but times a -1. And so when I add these two wave functions together, instead of getting a plus sign plus a positive part of my wave function adding to a positive part of my wave function and giving me an even bigger value of the molecular wave function, now I'm going to see destructive interference. So my positive region of this tail and my negative region of the tail that are in the internuclear region are going to cancel each other out partially. And that leads to overall destructive interference. And so you'll notice that when I either plot my value of the wave function, sorry, these right pictures are the wave function squared. I should be careful about that. So when I either plot my value for psi minus, or when I square the wave function, it's really important to notice that in this region of the internuclear region, I have a much decreased chance of seeing the electron. In a sense, this wave function is telling me that the electron density, if an electron is in this orbital, is going to be pushed to the peripheries of the molecule rather than concentrated between the molecular region. And so because I have one picture of this molecule, the Psi plus orbital, that's helping concentrate the electron density in between the two nuclei, helping them share electrons, we're going to start referring to this type of wave function as a bonding orbital. Conversely, because for my green function, the psi negative function, my electron density is getting pushed to the periphery, making it harder to share electron density, we're going to refer to this type of orbital as an antibonding orbital. And once again, with our app, I want you to see that we have our wave function that is slowly going to come together, and in this case, we're going to slowly move the slider to the left, and as our wave functions begin to overlap, you'll see this deconstructive interference and the resulting wave function. Again, the fact that we have two colors here is indicative of the fact that my wave function is positive on one half and negative on the other half of this wave function. And now it occurs to me I might not have done the slide transition right for my sigma plus orbital, so just in case, let me show you that separation again, where you can see our wave function slowly coming together, merging, and kind of at medium distance internuclear separations, forming a lozenge. Okay, great. And so sometimes it's helpful to have our two graphs for our probability density, psi squared, shown for both the bonding and the antibonding orbital. And I like this superimposed graph because it shows really clearly that in the two wave functions, our bonding orbital, shown in red, has a very high chance of finding the electron in the internuclear region, and our psi negative wave function shows an increased probability of seeing the electrons either very close to one of the two nuclei or outside on the periphery of the molecule. And so now we have two possible orbitals where an electron could be located. And if we want to think about where the electron is actually going to be located, we're going to have to determine what the relative energies are for these two different orbitals. So let's talk about what energies we would expect from both our psi plus and our psi minus wave functions. And I'm going to start with a qualitative argument and then end today's lecture with a more quantitative argument about the wave functions and the energies that you expect to see. And so first, let me draw one last time our psi 1s orbitals for our isolated atoms kind of superimposed on each other so that you can see how when I add these or subtract them, it'll eventually lead to my two molecular orbital wave functions. In an isolated atom, the electron density is evenly distributed to the left and to the right of the nucleus. And we're going to call this our reference energy, E1s, like we had at the beginning of today's lecture. When we get to our psi plus orbital, electron density is accumulating in this internuclear region relative to the isolated atoms. This has the net effect of increasing nuclear electron attraction because now if I have my electron showing up in this internuclear region, not only can it be attracted to HA, but it can easily be attracted to HB. And they're at very close distances. And it's very probable to find the electron in this region, making it an overall stabilizing effect to the orbital. So our bonding orbital, I argue, is going to be lower in energy than the isolated atom because an electron, on average, gets to be attracted to not one, but two nuclei. Conversely, in the psi minus orbital, electron density is depleted in the internuclear region. That means that my electron is more likely to be found over outside on the periphery. And compared to the isolated atom, well, we still have a nuclear electron attraction. That's good. The the attraction between my electron, as I've shown it depicted here, and the leftmost nucleus is really too weak to matter too much. But that means that my internuclear repulsion between my two hydrogen atoms is not going to be mitigated at all by an increase in electron nuclear attraction, and so this repulsion effect is going to be fairly dramatic, and it's going to destabilize the orbital relative to the isolated case. And so overall, the ordering of energies for my molecular orbitals is that the bonding orbital is lower in energy than the atomic orbital, and the antibonding orbital is higher in energy than the atomic orbital. Let's make this more quantitative because it turns out that there's a little bit more we can learn by actually doing some math for this problem. So for the H2 plus molecule, you can show that the energies of either the bonding wave function or the antibonding wave function are equal to a set of three terms. And my three terms are, first, E1s, that is the atomic orbital energy for the isolated system. So it's kind of nice, we can directly now compare our bonding orbital energy to our reference atomic orbital wave function energy just by subtracting or moving this first term over to the left-hand side of my equation. And so the two competing terms that are going to help me assess whether or not this orbital energy is higher or lower than its reference state is a red term representing nuclear repulsion. So notice this is just Coulomb's law. I've got two positively charged nuclei, each with a charge that's equivalent to the electron charge. And so we've got E squared over 4 pi epsilon naught times R in the denominator, capital R representing our bond length. And then there's a third term that I've shown in yellow that represents electrostatic interactions of the electron with one or more of the two nuclei showing up in the problem. I'm going to briefly go over what these terms, J, K, and S, showing up in my yellow term represent so that you can understand them from a chemical interpretation. And then we're going to plot these functions so that you can see how the energies of the orbitals vary as a function of bond distance. So of my three terms that are showing up in my expression all the way to the right, J plus or minus K divided by 1 plus or minus S. By the way, the plus or minus symbols in this case, every time you're talking about the bonding orbital, you should follow along the top line. So we're going to have J plus K for the bonding orbital divided by 1 plus S. And for my antibonding orbital, I'm going to follow along with these negative signs. So I'll get J minus K divided by 1 minus S. So J represents our Coulomb integral. And the form of the integral is shown on this lecture slide. You don't necessarily need to write it down. But what it represents is the interaction of nucleus B with the electron density on atom A. So in other words, if the electron starts on atom A when my atoms are separate, and I slowly move them closer together, before electron A has a chance to move, the Coulomb integral tells me how strongly it'll be attracted to the nucleus on hydrogen atom B. K is an integral that represents the overlap charge density, or if you like, the exchange integral is what it'll be called in theoretical chemistry. Again, you can see its mathematical form, which I'm not going to dwell on a lot, so much as its chemical interpretation, which is that K represents the increase, if we're talking about the bonding orbital, or the decrease for the antibonding orbital, of the electron density in the internuclear region and the corresponding interactions with the two nuclei. So we paid a lot of attention in our visualization to how in the internuclear region there was an increase of electron density there, and K tells us what the strength of interaction that is, or how much benefit we get from having that accumulated electron density in the internuclear region. Last but not least, S is called the overlap integral, and it represents the extent to which these two integrals, or the extent to which my two wave functions, H on HA and HB, are overlapping with one another. And so S tends to be large in the internuclear region where you get a lot of overlap between the wave functions, and small elsewhere. And as you might expect, if I shrink capital R, these two wave functions are going to interact more and more, and S is going to get bigger and bigger. So for this overall bonding orbital to be a net attractive interaction, to be a net benefit to the system, such that my two separate H atoms would want to form H2 rather than staying separate as a neutral H atom and an H plus cation, we need to make sure that this second term, which I'll circle in red, this nuclear repulsion term, is smaller than my third term, representing overall, hopefully beneficial electrostatic interactions. And so let's go ahead and plot what these look like so that we can see the various integrals and then see what the overall effect is on E plus and E minus. And so shown here, and let me zoom in a little bit so that we can really see it, is the shapes as a function of capital R, our internuclear separation, of my S, J, and K integrals. So you'll notice that S ranges from 0 to 1, showing that at large internuclear separations, there's no overlap between the two wave functions. And if I put the two nuclei on top of each other, there'll be perfect overlap between the wave functions. J represents a Coulombic interaction, and that means that even when our electron is fairly far away, when our two nuclei are separated, this electron sees for quite a long time what this other nuclei is doing and is attracted to that nuclei. J will eventually decay to 0, but you can see from the graph that it decays to 0 pretty slowly compared to my K and my S integrals. So we can say that it decays to 0 slowly. And then last but not least, my K integral also decays to 0 actually pretty rapidly, because unless these atoms are pretty close together, there's not going to be a whole lot of overlap, and therefore not a lot of potential electron density buildup in the internuclear region. But K is going to decay to 0 pretty rapidly, but it also, for both the J and K integrals, will at shorter separations start to approach to -1. So in the limit that R goes to 0, K equals -1, representing that for both of these integrals, the closer the atoms are together, the better for increasing favorable interactions between the electron and the nuclei. But let's go ahead and get to the punchline, which is what is the interaction what does the energy profile look like for my bonding and my antibonding orbitals? And so this graph shows exactly that. Again, we have R being plotted on the x-axis in units of Bohr. And we also have put this graph into a form where it's showing us delta E rather than E, so that you can see how the energies of these orbitals look relative to the isolated case. If the energy of an orbital is less than 0, that represents that forming this molecule leads to a stabilization of the energy, a lowering of the energy, and that would suggest that this molecule does want to form at equilibrium. On the contrast, if my orbital energy is higher than 0 on this plot, that means that the energy of this orbital is higher or less stable compared to the isolated atom, and that would suggest that this atom does not want to form. And so what's really interesting about these bonding and antibonding orbitals is that for most internuclear separations, not all, you can see that if I put my hydrogen atoms too close together, even the bonding term is not favorable because the nuclear-nuclear repulsion is going to get far too big to stabilize this molecule. But at medium internuclear separations, we can see where the minimum is for this bonding curve, somewhere around 2.6 Bohr, or if you like better, 1.3 angstrom. There is a stabilization effect for these two atomic orbitals merging together and forming a bonding molecular orbital. And so there should be a couple of really important takeaways from this graph that I want to highlight for us. The first takeaway is that the relative energy of the bonding orbital is negative, except for at fairly small internuclear separations. And where this bonding orbital is at a minimum is going to dictate the desired equilibrium bond distance of the molecule. So we can predict from this molecular orbital theory that the H2 plus molecule is going to have a stable bond length of around 1.3 angstrom. And you can do the experiment on the H2 molecule, on the H2 plus molecule, and you'll find that the actual experimental bond length is something closer to 1 angstrom. So we're not doing perfect with this simple theory, but we are qualitatively being able to predict the bond lengths. A second takeaway that I want us to see is that the relative energy of the antibonding orbital is always positive. There is no place where this blue curve dips below zero. And so that means that the antibonding orbital is always a destabilizing interaction relative to the original atomic orbitals. And that destabilizing interaction you can see it's kind of getting exponentially worse as we get closer and closer to having these nuclei be on top of each other. And that leads to my third takeaway, which is that at any internuclear distance, the antibonding orbital's destabilizing effect is larger in magnitude than the bonding orbital's stabilizing magnitude. And I was taught the little catchphrase, antibonding is more antibonding than bonding is bonding, but you can use whatever mnemonic you like to help you remember this. Just I want you to see from the graph that the blue curve is always more destabilizing than the red curve can be stabilizing. Okay, and so what that means for us is we can start to make really practical claims about how many electrons could be present in a molecule that is composed of these bonding and antibonding orbitals. Putting electrons into bonding orbitals helps stabilize a molecule. Putting electrons into antibonding orbitals is going to destabilize the molecule. And because the antibonding orbital is worse than the bonding orbital is good, that means that putting too many electrons into these antibonding orbitals is going to lead to the molecule dissociating and being at equilibrium more in a more favorable state as isolated atoms. And so let's use this information to tackle the two questions that we presented at the beginning of lecture. What is it that makes an H2 molecule stable? And what is it that makes a helium diatomic molecule unstable? To do this, I'm going to show you a technique, a style of drawing that's called an MO diagram. And in an MO diagram, we are going to draw a special type of energy level diagram that helps depict the relative energies of the bonding, antibonding, and original atomic orbitals. And so to do that, let me go ahead and start drawing on my energy level diagram a line to represent the bonding orbital. It's always helpful to label these orbitals, and so I am going to denote for myself that this orbital is my sigma plus orbital. You'll also see a lot of folks try and draw the shape of the wave function. And so remember, from our contour plots, the shape of the wave function looks something like this. And so on my piece of paper, when I'm trying to draw the shape of this wave function, I'm going to draw my bonding orbital looking like this. I always like to draw little dots to represent the positions of the two nuclei. And so this would be a hand-drawn picture of what my molecular orbital looks like for the bonding orbital. Next thing that I'm going to do is I'm also going to draw on my energy level diagram the location of the antibonding orbital. So here's my antibonding orbital. Label it sigma minus. And now I need two colors to depict this orbital because there's both positive and negative signs of the wave function showing up. And these are very qualitative diagrams. If you're like myself and you're not a very good artist, That's fine. You can either use shading or two different colors to represent this. But my positions of my two nuclei, I'm going to try and leave them pretty similar. Remember, I'm trying to indicate in this antibonding orbital that a lot of my electron density is pushed to the outside of the two nuclei rather than being between them. And I need to use those two colors to indicate both that there's not very much electron density in the internuclear region. You can see that because our boundary surface diagram sort of excludes some of that internuclear region. And also, it helps me see that there's a node in between these two nuclei. All right, so far this is looking very similar to a standard or traditional energy level diagram. What makes it a molecular orbital diagram is that folks will also show on this diagram to the outside what the original atomic orbitals looked like. And by convention, we're going to put one of the atomic orbitals for HA on the left side of the diagram and one of them on the right side of the diagram. And looking back up at my graph, I'm going to put the energy of my reference energy much closer to the energy of my bonding orbital than to the energy of my antibonding orbital. Again, because antibonding is more antibonding than bonding is bonding. And so I'm going to choose to put them, again, this is still a qualitative diagram, so I'm making an educated guess a little bit based on the shape of the graph and trying to replicate it to the best of my art skills. I'm going to put my two orbitals to the left and to the right, and I'll label my diagram as being, here's HA and its energy level diagram, here's HB and its energy level diagram, and here is my H2 plus molecule. And the last things that I need to do for this diagram is, one, I need to label my other wave functions. Two, by convention, any orbital that forms as a linear combination, you use dashed lines to indicate that that atomic wave function is contributing some of its character to the orbital. And so since both of my atomic orbitals are contributing to both of my molecular orbitals, these are the dotted lines that I'm going to draw on this molecular orbital diagram. I'm going to try and scooch this just in a little bit closer so that it looks symmetric. Okay, and then I also like to draw pictures of these orbitals. So I'll put my two nuclei together. For the 1s orbital on atom B, I'm just going to draw a circle around the rightmost nuclei. And for my orbital that shows up on atom A, I'm going to just draw a circle around the red nuclei. And so my molecular orbital diagram helps me see the energy levels, helps me see the shape of the orbitals, and helps me see what the relative stabilization is that I can get from forming a molecule. So I have one more thing that I need to do before I'm done with this molecular orbital diagram, and that's to populate the diagram with electrons. Now, we have one electron in this system, so in my molecule, there's going to be one electron. The same rules for populating an electron diagram in the atomic case are true for the molecular case. We're going to obey the Aufbau principle, Hund's rule, Pauli exclusion principle. And so, by convention, you also draw the electrons on the outside of the diagram. And it doesn't matter so much where you put them, as long as it, to the best of your ability, makes chemical sense. And so I, for charge balance, need to decide which of my atoms I'm going to make the H plus cation and which of them I'm going to make the HA atom. I'm just going to make atom B my cation, and that means that before I form my molecule, HA also has one electron. And you'll notice that a good feature and a good check for your molecular orbital diagram is the total number of electrons on the outside of the diagram should match the total number of electrons shown on the inside of the diagram. Okay, So now this is a complete version of a molecular orbital diagram for the H2 plus molecule. And what we notice is that because all of my electrons are in bonding orbitals, they are more stabilized compared to having my individual atoms. So forming this molecule is a favorable process. And H2 plus, just like this molecular orbital diagram predicts, is a stable molecule, and it has a bond length close to an angstrom. And so MO theory is a good qualitative way of trying to understand the bonding behavior of molecules. This is not something that Lewis theory would have been able to predict, right? Because what do you do to draw a Lewis diagram of a molecule where there's only one electron? Don't you need two electrons to form a bond? So MO theory is a little bit more robust in this case in helping us predict somewhat strange molecules and knowing that they actually are able to form in real life. And the last thing I want to leave us with for today's lecture is, what about other molecules? How are our MO diagrams going to change when we start talking about H2, or the hypothetical unicorn, the helium diatomic molecule? Well, qualitatively speaking, the shape of the MO diagram, the arrangement of the different energy levels, doesn't change, but the number of electrons does. And so what I've shown on these diagrams, I haven't shown pictures of the wave functions, but I have shown the various energy levels in my diagram. And for the H2 molecule, because I have a total of 2 electrons, both electrons are going to go into the bonding orbital of the H2 molecule. This is more stable even than the H plus and the H2 plus molecule. And so our bond length, it's going to be snuggled up a little bit closer. Our H2 bond length is about 0.75 angstrom. And the way that mathematically I'm visualizing whether or not there's an overall stabilizing effect or destabilizing effect, to make explicit note of this, is what I'm comparing is the energy of my overall system, which is the energy of the first electron in this bonding orbital plus the energy of the second electron also in the bonding orbital. And that's less than the 2 electrons both in individual 1s orbitals. So that's where we get that H2 is a stable molecule relative to the isolated atoms. On the other hand, for helium, now I have 4 total electrons that I need to put in the system. The first 2 electrons that I place into the bonding orbital seems like it's on the right track. That's helping stabilize the molecule. But then I have to put the other 2 electrons somewhere. They go into the antibonding orbital. And because antibonding is more antibonding than bonding is bonding, that means that the overall energy of this system is higher than that for just having my 2 helium atoms separate, not forming a molecule. And so that helps explain to us why it is that helium is not going to form a diatomic molecule. It is not stable relative to the isolated atoms. And so hopefully this is giving you a starting window to think about how small molecule activation could be explored through the lens of molecular orbital theory. Today, I want to stop here, and we'll pick up talking about some slightly more complicated molecules in upcoming lectures. But hopefully what you've seen in today's lecture is a few important takeaways. First of all, MO theory uses a linear combination of atomic orbitals to generate molecular orbitals. Our 2 available linear combinations are either to add together the 2 orbitals or to subtract them, and that leads to either a bonding orbital in the case of addition or an anti-bonding orbital here in the case of subtraction. Because the bonding orbital accumulates electron density between the 2 nuclei, it leads to a sharing of electrons, and that stabilizes the orbital, and we say that bonding orbitals are more stable, or they help form a molecule. Conversely, an anti-bonding orbital pushes electron density away to the outside of the internuclear region. It lessens electron sharing and it destabilizes the molecule. And last but not least, we showed a first example of how to use this information to draw an MO diagram of molecules built up from first row elements, hydrogen and helium. The electron filling rules are the same as they were for the atomic case, but using our MO diagram, we were able to successfully predict both the existence of the H2 plus molecule, the stability of the H2 molecule, and the lack of stability of the He2 molecule, showing, again, incorrect prediction with experiment, why certain molecules will form or not form. And so that's where I want to leave us with for today, and I look forward to seeing you all in class so that we can go over and practice a little bit drawing these MO diagrams. I also hope that you look forward to some of the upcoming lectures where we're going to talk about elements on the second row of the periodic table and start to address some of these questions about small molecule activation that we weren't able to explore through a lens of Lewis theory. So with that, take care, and I look forward to seeing you all in class.